Swayam Prabha. Digital India. Educated India.
Welcome to this session on applications of microwave processing of materials under the course Advanced Manufacturing Processes. In the previous session, we have discussed about the introduction to microwaves, their characteristics, their features and the background of microwave processing of materials, how the microwaves interact with different types of materials like reflecting materials, absorbing materials and transparent materials. In this session, let us move ahead with some more applications of microwave in material processing. Like as I have already indicated in the previous session, microwaves can be used for heating purposes, microwaves can be used for enhancing the chemical reactions, microwaves can be used for curing of polymers and so on. Now, let us look at these with some more details, particularly putting more emphasis on engineering applications like metallurgical applications in sintering, in joining, cladding and so on. Let us brush up the unique features of microwave processing. We have already indicated in the previous discussion. The first and foremost feature of the microwave processing is penetrating radiation. Unlike the conventional heating, in which the heat waves move from outside the surface of the body or the object to be heated up or the processed. In case of microwave, it penetrates throughout the volume or it gets reflected, as in the case of reflecting materials or reflecting mirrors. In that case, no processing is possible. Processing is possible only when the material is absorbing and it penetrates throughout the volume of the material. This is one of the important features of microwave processing. Then second is controllable electric field distribution. This also I have already indicated that we can have better control as far as the electrical field is concerned, since we need to apply one electric field at a particular frequency. We can have better control of this electrical field and the power absorption, as I have already indicated in the previous discussion itself. Power absorption, say P, is a function of frequency of the applied microwave, then the dielectric losses of the material. So, this is material and electric field applied. So, this is regarding the radiation or the microwave frequency or the microwave, we can say. So, this is regarding the material. So, this to be processed say this is to be processed, and this factor is nothing but the applied electrical field. So, this gives us flexibility for controlling. So, therefore, the power that will be dissipated or absorbed in microwave, so will be influenced by this electrical field, this E. Now, as we know, all of us know, as far as the control of the process is concerned, so far as the quantity is electrical quantity, it is easier for us to control the process. So is the case with microwave processing of materials. Then another feature is very rapid heating. As we know, microwaves travel in the speed of light. So therefore, penetration is taking no time as far as the realistic product volumes are concerned. And if the material is absorbing a material, then the interaction becomes very fast and heating becomes very fast. Then another important and very significant feature of this processing is the differential coupling, that means the selective heating. This what is the meaning of this selective heating? So, this can be explained like this. Suppose there are two materials in this, and this is exposed to microwave. And this is material to be heated, or we can say processed. Now, microwaves are falling on this material as well as on this material. That means, both the materials we are exposing to microwaves. But the significant thing is that depending on the properties of these two materials. So, this is one material, say M1, and this is another material M2. However, the properties of M1 are not equal to properties of M2. Therefore, as we have already seen, the heating is a function of one other among other factors, dielectric loss. This is a material dependent factor, as I have already indicated, and since these properties are not equal, therefore, the effect of heating on these two materials will be different. Rather, we can understand this in this way: both the materials will not get affected in a similar fashion by the incident microwave energy. In other words, the materials will get heated up in a different way. This is the very reason why, while heating some material, say cup of water inside the microwave oven, we can hold the cup very comfortably even though the inside material is very hot. That means, water is getting heated faster rather than the material that contains water. Of course, if the container also a microwave absorbing material, then it will be a different case. Then the container will also get heated up. Therefore, I would request not to experiment this without knowing the material properties inside the home microwave ovens. One need to know which are the microwave friendly materials or which are the microwavable materials. That means, they do not get heated up while exposed to microwaves and microwaves. So, please be careful while experimenting with yourself, rather do not go for it until and unless you have sufficient information on this. One material may be very hot, one may be at room temperature, or both may be very hot. For that matter, it is not a question of one or two materials, rather we can keep number of materials together, but the heating on these materials will take place according to their own material properties, and therefore, the degree of heating in those materials will be according to their material properties. This is called selective heating or differential coupling. Now, let us quickly look at the benefits of microwave processing as well, very quickly. As we have already indicated, cost saving, this is one of the important aspects of microwave material processing. This cost saving we can derive in terms of time saving. Time saving is nothing, time is nothing but cost, energy saving, and of course, reduced floor space, because in a very limited space we can have very high energy output in terms of electromagnetic radiations or microwaves. Then the microwaves can have rapid and uniform internal heating. This we have already discussed in details, how uniform heating can take place while exposing to microwaves. Then precise and controlled heating, then improved quality and properties. These terms are also being discussed already. Then another feature is their environment friendly and clean process, unlike some other conventional heating process, heating furnaces etc., where conventional heating or burning of some fuels may be required. Of course, in induction heating it is not required. And then potentially to process materials or products that are difficult or impossible to produce reliably by conventional methods. So, this microwave processing may work better in those cases. Now, let us come to the applications of microwaves. In material processing, the application of microwaves was not very popular, particularly for engineering materials processing. It has been popular for food processing, but if we look at the history of microwaves, they were basically developed for communication purposes, and still they are going strong. In almost all communication equipment use microwaves extensively, even the mobile communication, satellite communication, people use microwave very extensively. Then another reason for which these microwaves were developed in the early years were food processing or cooking food, then tempering and thawing, then curing of wood and rubber etc. These were some of the earlier applications of microwaves. However, application of microwave energy has now been extended to many other areas. This includes number 1, sintering of ceramics, composites and metals, then joining of ceramics, composites and metals, then controlled nucleation and crystal growth, then number 4, drying and synthesis of materials. As I have already indicated, there need not be heating always associated with microwave processing, but could be synthesis as far as the reactions are concerned, chemical reactions are concerned, or curing of polymeric composites are concerned, or some deriving some chemicals, new chemicals with the synthesis. This microwave exposure can be very useful tool. Then some areas using microwave effects, also called non-thermal microwave effects, such as enhancing chemical reaction rates, then structural densification, enhancement in material diffusion, these microwaves can be used. These are some of the aspects. Even today scientists are yet to offer some acceptable explanation regarding what happens or the mechanism, how it happens. People have seen, or scientists have seen, the effect of microwave radiation on some chemical reaction is taking place or enhancing the reaction rate, etc., but unable to correlate with some known facts or known phenomena. So, this we call at this moment we call microwave effect. Maybe with further research within few years these things will be able to be explained. Now, let us see some of the industrial applications of microwaves. In the 1970s and 80s, microwave processing was mostly confined to absorbing materials and food processing areas. Until the year 2000, microwave processing of materials was mostly confined to ceramics, semiconductors, inorganic and polymeric materials. Now, there are different other areas where microwaves are being very widely used. Some of the common applications include, these are say for food processing, baking. So, baking of potatoes, cakes and so on. So, or cooking some foods, common food items, this is very common application of microwaves. Then for chemical reactions to initiate or to complete, this microwave exposure is being used. Say for example, neutralization of toxic substances, devulcanization of scrap rubber, pyrolysis of wastes, oxidation of sulfur and so on. So, in cooking, cooking of food grains, vegetables, meat, fish and so on is very useful or very effective. Then another very useful application of microwave is like curing or hardening of polymeric composites, polymeric materials. These polymeric materials include polyvinyl chloride or PVC in short, polyurethane foam like puff what we call, then epoxy resin, polyester, plaster of Paris, cement, cellulosic membranes, wood gluing with adhesive, then epoxy laminates, bakelite and so on. Then for dye fixation, the microwaves can be used for yarn or fabrics. Then for drying, so drying of paper, film, coating, casting molds, ceramic powders, pharmaceuticals products, wood, coke and so on. Then there is one process have been this has been developed by Macmillan Bloedel. So, in this process is called parallel process. In this process, the penetrating nature of microwave energy is used to rapidly and uniformly cure thick cross sectional polymer, wood, composite beams as they are protrude continuously through a die. As most of us know, the pultrusion process, which is mostly used for processing of polymers or polymeric composites. Basically, for polymeric composites, pultrusion is a process. So, in this process, along with this pultrusion, we can use microwave energy where the material will get cured almost simultaneously. Now, let us discuss a few major applications of microwave processing in details. These processes include sintering, joining, cladding, which are very important areas where application of microwave energy has been found to be substantial. Let us discuss some of these processes briefly. Let us first take sintering using microwaves. As we know, sintering is a process quite commonly used in powder metallurgy process. Conventionally, it involves heating a powder or a powder mix in a blended form in a furnace, so that it acquires the necessary strength. Tinga and Voss, these are the two scientists, they first reported the use of microwave for sintering of ceramics in the year way back 1968. Consequently, thereafter several researchers continued work on sintering using microwaves. Another scientist called Nishitani in the year 1979, he has found that by adding a few percent of electrically conducting powders, the heating rates of refractory ceramics can be considerably enhanced. In the last session itself, we have discussed ceramics are transparent materials as far as the microwave energy is concerned. However, as we have indicated, if we mix some materials which are microwave absorbing materials into these ceramics, then the heating rates can be enhanced. Those absorbing materials will be responsible for absorbing the microwaves, and then that heat will try to hit the ceramics initially, which will make ultimately the ceramics also as an absorbing material at higher temperature. It was only in the year 1998 that Professor Dinesh Agrawal and his co-researchers have attempted to microwave sintering of metal stills FC208 and FN208 to near net shape. In the year 2000, Agrawal and his co-researchers have reported the sintering of powder metals, pure metals, alloys and intermetallics in a microwave field in 15 to 30 minutes. Later, in the year 2004, the sintering of tungsten and its alloys was successful through microwaves at 1400 degrees Celsius in 20 minutes, and by the year 2008, sintering of molybdenum to full density at the temperature of 1650 degrees Celsius was achieved in less than 5 minutes. Then sintering of aluminum was also reported in the year 2008 at 630 degrees Celsius in 1 hour duration. Let us see some more research findings as far as the sintering is concerned. One work was reported by Zhu and his co-researchers in the year 2009. They worked on sintering of tungsten, nickel and iron powder at varying heat rates and heating rate of 80 degree per minute they have found to be the best for the microstructure and mechanical performance. Then another group of scientists like Mondal and his co-researchers in the year 2008 attempted sintering of pre-mixed and pre-alloyed 90 tungsten, 7 nickel and 3 copper powder through microwave and conventional way. They have found that higher density, higher micro hardness and fine microstructures without any micro cracks for this microwave sintered products. Then Padmavati and his research group carried out sintering of 316L stainless steel and ferritic stainless steel, that is 434L, through conventional and microwave mode of heating with 1.5% graphite addition. They have found that higher corrosion resistance and improved corrosion properties with this microwave sintered products. Then again Padmavati and his group reported in the year 2008 sintering of aluminum, magnesium and solar alloys. The tensile testing of these sintered products showed better properties in the microwave sintered conditions than the conventionally sintered ones. Then another group, Rajkumar and Aravindan, in the year 2009 they have reported about copper graphite composites by heating in a hybrid mode, and they have found there is no crack in the composites while doing so. Then another group, Chiller and his co-researchers, they have sintered molybdenum powder and they could achieve 98% of the theoretical density in these sintered products, which is quite substantial. Then Sunil Ratna and his co-researchers developed sintering of micro and nanocrystalline tungsten carbide and 12 cobalt powders through microwave. They have found that the samples of microwave sintered samples yielded slightly better properties when compared to the conventionally sintered products of the same material. Now, let us move on to another application of this microwave processing of materials, which is mostly the engineering application, that is microwave joining of non-metallic materials. Trans Welding Institute successfully used the modified microwave multimode cavity for welding of polymers. They carried out this welding of the polymers using microwave energy at 2.45 gigahertz of frequency. They have designed the applicator to be capable of irradiating the entire component and produce complex 3D joints, which was considered to be difficult one as far as the other techniques are concerned. But the encouraging factor is that the welds were created in less than 1 minute, which is quite substantial. Then microwave heating has been extensively used for joining of ceramics and ceramic composites as well. There have been lot of work reported in the recent literature. Iftikhar Ahmed and his co-researchers in the year 1997 could join silicon carbide ceramics and composites using polymer precursor at 1000 degrees Celsius in 1 to 1.5 hour of duration. Then Iftikhar Ahmed and Elias, they have reported in the year 2001 about the microwave joining of 48% alumina, 32% zirconia and 20% silica ceramics, and they have found that it yields higher joint strength than the best material even. Then Meek and Black, they have also reported joining of alumina and alumina ceramics using commercial scaling sealing glass in between the two materials, that is also called the interlayer, and they have reported it in the year 2001. Then Binner and his group of researchers have reported the joining of alumina, silicon carbide and yttria doped partially stabilized zirconia rod in the year 1995. In India in the year 1999, Aravindan and Krishnamurthy successfully joined sintered alumina 30% and zirconia ceramics using sodium silicate powder as an interlayer. Then another important development in this microwave joining is microwave joining of bulk metals. In spite of significant progress, there has been hardly any detailed report on microwave joining of metallic materials. The main reason was due to the misconception, which was removed recently, that all the metals reflect microwaves and cause plasma formation. So, this was also explained in the last session. As this curve is shown in the screen, we can see. So, this is the power absorbed per unit volume of the materials. So, this is very high for water and low for materials like alumina, thermosets, thermoplastics, etc. This alumina is nothing but a ceramic, and also it is low for the materials like aluminum, copper, silicon, steel and so on. These are metal based materials and they are considered to be the reflecting materials, whereas the other extremes materials like the ceramics etc. are considered to be transparent materials. Only these materials like water etc., they absorb material with high degree of absorption. Thus, these metallic materials to be processed with or using microwave is a challenging task. Salom and his co-researchers in the year 2005 have reported the brazing of gamma titanium aluminum and silver based filler materials. Barmach and his group have patented the brazing of titanium carbide tip to diamond cutter at 1000 degrees Celsius by using brazed powder as interface layer in the year 2000. Siros and Diego in the year 1995 have reported the joining of thin steel specimen in the range of 0.1 to 0.3 millimeter in an inert atmosphere. Then again Agarwal and his group in the year 2006 have reported joining of regular steel and cast iron in a microwave field using some braze alloy in 2 to 3 minutes. Then let us come to some of the developments in microwave joining of bulk metals, and these developments have taken place in IIT Roorkee itself in the microwave material processing lab. This has been reported for the first time by the IIT Roorkee research group, in which fortunately I am also a member of the group. The microwave joining of bulk copper has been carried out, microwave joining of steels have been carried out, microwave joining of steel to mild steel has been, stainless steel to mild steel have been carried out and so on. This is in the screen, some specimens are being shown. So, these are the plates of copper and they are being joined using microwave radiation in this. We can see some of the specimen being joined by microwaves using this stainless steel materials. So, these are stainless steel plates, they are being joined here. These are 316 stainless steel. So, they are being joined in microwave processing laboratory by using 2.45 gigahertz microwave. So, this is the joint zone, we can see joint zone. So, this is the base material and this is the base material, say stainless steel. So, in between the researchers have used some powder layer in that is also called interlayer, which is called interlayer in between. So, this thickness in between this will be something around 50 micron in between. That means, this interlayer between these two materials are very, very thin. So, this can be explained like this. This is one of the plates, say this is a stainless steel plate, then another plate is like this, they need to be joined. So, this is also another plate. So, we can say these are the plates to be joined, say SS plates, stainless steel plates. In between we are keeping one interfacing layer. This is called interfacing layer. So, this is nothing but a powder layer. Then this material will be covered, this material will be covered by some other material, so that while exposing to microwave, these metallic surfaces do not reflect the microwaves and cause harm to the equipment, and the microwaves will fall only to this layer, and therefore, this layer will get heated up, they will get melted, then the very nearby to this powder layer will get melted and there will be a bond formation between them. This distance I am talking about that gets melted of the parent material will be something around 10 micrometer only. So, something less than or equal to 10 micrometer only, and this interfacing layer. So, this will be something around 50 to 100 micrometer thick. That means, we can think about how thin this layer is and how thin this heat affected zone or the melted zone of the original material is. That shows the preciseness of this technique and the usefulness of this technique. This figure. So, this is the layer in between, the powder layer which got melted during heating, and then on cooling they got the structure something like this. Whereas, this we can see the relatively different microstructure, these are the base materials or the parent materials which are being joined like this. And upon comparison with TIG welding, we have found to be these joints almost to be equivalent as far as the strength is concerned. However, in some cases bending strength is found to be less than the TIG counterparts or the TIG joints, but in most of the cases the elongation is more. And significant thing is that the porosity in this joint, porosity is very, very less. As we know, porosity is nothing but they are pockets of defects, but in these cases the porosity is something close to 1% only or less than 1%. Whereas, in case of TIG welding etc., we have seen porosity can be 4%, 3%, 5% and so on, and higher the porosity we should say inferior is the joint, which we have found in case of microwave joining to be very good. Next comes another application which is emerging application, not these techniques are very recent developments and say only one year or 2 year old only, and they are yet to come to the industries to be adopted, but we are confident that this will come very soon to the industries as well. And this technique is also being developed in the IIT Roorkee laboratory, and some patents have been claimed for both microwave joining of bulk metals and microwave cladding of metallic materials as well. The development of coating and cladding using microwave have been very limited globally. In the last decade, only few research groups have reported their works on microwave coating as well as in cladding. Only few of them are listed here, very notable few. One work is reported by Das and his co-researchers in the year 2008. So, they have reported about coating with microwave exposures for 60 minutes and 90 minutes, which is quite high, considered to be quite high, and they have obtained porous thin coating something around 42 micron thick, and dense and thick coating something around 0.6 mm thick of aluminum oxide on aluminum substrate. Then another work being reported by Camerota and his co-researchers. So, they have irradiated titanium substrate with nickel aluminum coatings to obtain nickel aluminum coating, and they could obtain good results on titanium substrate. Another group, Borman and Saylor, so they have successfully developed coating for titanium and aluminum alloy using microwave radiation. They have reported the coating of friction reducing alloys using copper nickel indium powder on titanium 6 aluminum 4 vanadium alloy, and they have found better properties of microwave induced coatings. Then some recent developments in microwave cladding on metallic substrates. So, after some trials, it was found that it is possible to develop metallic coating with substantial thickness on metallic substrates through novel processing technique known as microwave hybrid heating. Recently, tungsten carbide and cobalt clad and UAC clad on stainless steel have been successfully carried out using home microwave applicator at 900 watt on using 2.45 gigahertz microwaves, and this was being carried out in the microwave material processing laboratory at IIT Roorkee. The developed clad is found to be well metallurgically bonded with the metallic substrate. The clad is free from any visible cracks, and also the clad contains significantly less porosity, which is almost 1% and which is substantially less. So, this is an image of the clad being developed. So, this is the image of tungsten carbide and cobalt clad. So, this is the substrate we can see in the screen. This is the substrate, that is stainless steel substrate, and this is the clad. So, we can see a very homogeneous microstructure of this clad, and there is no visible crack, no visible porosity. That means very uniform cladding without much of defect, and this was being produced in the microwave applicator of only 900 watt capability at 2.45 gigahertz, and this was of course fabricated in less than 10 minutes of duration. As we know, tungsten carbide is one of the very strong materials and very high temperature melting point, high melting point materials, and this is a very good material as far as the wear resistance is concerned. So, therefore, tungsten carbide cobalt material combination as a cladding material is very good as far as the industrial applications is concerned, and that could be developed using microwave energy. So, this is the cross section wise how the clad looks like. So, we can see this is the substrate, that is a stainless steel substrate, and this is the clad material, and we can see there is a very smooth transition of this joint. That means the cladding, that means the metallurgical bonding has taken place between the substrate and the clad material. There is no mechanical bonding sort of things that exist in case of coating, and that is how they become little weak. But here it appears to be as an integral part of this substrate material itself, although there will be little property difference between them as the cladding material is different. So, this is the UAC material and this is the stainless steel material, and UAC is also known for very good wear resistant material, and therefore, UAC material cladded on stainless steel could be a very good industrial solution as far as this is cladding is concerned. Now, let us summarize what we have discussed in this session. We have discussed the advancements in microwave processing, various applications of microwave processing, and then in particular sintering, joining of ceramics, joining of bulk metallic materials, and then cladding of different materials on bulk metallic substrates using microwave energy we have discussed, and these are very significant applications of this microwave material processing in the years to come. We hope this session was informative and interesting. Thank you.